Today I'd like to show you a new equation that we can use with projectiles, and I'm calling this lecture 6.2. It is not section 6.2 in the Glencoe book, but it's my second lecture on projectiles. This equation is for the situation when something is thrown, hit, tossed, kicked from a level and it lands at the same level. We call this the range equation, and the range is just a particular dx when your heights on both sides are exactly the same. That is the only time you can use this. You need to know the angle, and you're going to know the initial velocity that the ball, let's say, is kicked at. So this equation looks like this. R is for range is equal to 2 times the velocity squared, sine theta, cosine theta, all divided by g, and g will always be positive. Again, this range is just a particular dx. It's a horizontal distance. So you want to write this on your equation sheet, and let me give you at least one example. So in the first one, we have an arrow shot 33 degrees above the horizontal, and its velocity is 45 meters per second. And it hits the target. What is the maximum height the arrow will attain? And B, the target is at the height from which the arrow was shot. How far away is it? So we have an arrow. It's shot at 33 degrees, and its initial velocity is 45 meters per second. So I'm going to list V as 45 meters per second. My angle is 33 degrees. Now, we're going to need Vy. So I'm going to have us go ahead and find that right now. And Vy, remember, is the sine of 33 degrees is equal to Vy over hypotenuse, which is 45 meters per second. And this value in this problem is 24.5 meters per second. So we have a y value, and our Vy, and this is Viy, our initial vertical velocity, is 24.5 meters per second. We have Ay is 9.8, and we'll need to work with that soon. So our first part is, what is the maximum height the arrow will obtain? Well, our Viy is 24.5 meters per second. It's in the upwards direction, so we need to make gravity negative because it's going to decrease the velocity of the arrow through time. And we're trying to find dy. Now let's go to the next page and draw another picture of this. So on this guy, your arrow's going up. Think about the velocity right here. That's your final velocity in the y direction, and it's 0. We just calculated Viy, and we said it was 24.5 meters per second for this problem. This is 33 degrees. And we're trying to find maximum height. Well, that maximum height is dy. We know gravity is acting against it, so Ay is negative 9.8 meters per second squared. So I would like to use the basic equation. I'm going to put Vfy squared equals Viy squared plus 2Ay dy, because everything is in the vertical direction. we're solving for dy. So rearranging and isolating dy, I have dy is equal to your final velocity in the y direction minus your initial velocity in the y direction squared, all divided by 2a subscript y. Vy is 0. VIY is 24.5 meters per second. Remember, we need to square that. Divided by 2 times negative 9.8 meters per second squared. Do your calculations. And you should calculate 30.6 meters is the height. I'm just going to write out here, dy equals 30.6 meters. The next question was, the target is at the height from which the arrow was shot. How far away is it? So we shot our arrow here. The target's at the same level. Remember, the angle was 33. And they gave us an initial velocity, which is tangent to the point where the arrow is shot, and that is 45 for this problem. So we can use our new equation because we're trying to find dx, which is, when it begins and ends at the same level, a range. So our new equation tells us the range is 2 times the initial velocity squared times the sine of theta cosine theta divided by g. So we have 2 times 45 meters per second squared multiplied by the sine of 33 degrees, the cosine of 33 degrees, and divided by 9.8 meters per second squared. So do that on your calculator. See if you agree with my answer. I have 189 meters is how far the arrow flies. So that's a use of our new equation. Let's do one more problem. In this problem, it's a soccer ball, and it's kicked at ground level with a speed of 15 meters per second at an angle of 20 degrees to the horizontal. A asks, how far does the soccer ball go before landing? B, how long is the ball in the air? And C, what is the maximum vertical distance the ball reaches? So, part A, how far does the ball go before landing? So, let's see if I can just get rid of that. I guess not. And there we go. Our soccer ball has a velocity of 15 meters per second. So let me just write, velocity is 15 meters per second, and the angle is 20 degrees in this problem. Our soccer ball's being kicked like this. Here's the 20 degrees, and we're looking at 15 meters per second is tangent to where the ball was kicked. All right, that's V. Not Vx, not Vy, it's just the initial velocity. So part A asks for the range, and range is 2v squared sine theta cosine theta divided by g. So plugging in our numbers for this problem, we have 2 times 15 meters per second squared. Remember that squared, it's really easy to skip that. Sine of 20 degrees cosine of 20 degrees divided by 9.8 meters per second squared. Do your math. Check your answer with mine, and it's 14.8 meters is our range, or our dx. Part B asks, how long is the ball in the air? So we need to find, let me just fix these guys. For part B, I can do it a couple of different ways. Now, we just found the range, and the range was equal to 14.8 meters. Now, if I go back to my original diagram, my velocity was 15 meters per second, and my angle was 20 degrees. If I find Vx, I'll be able to use my basic velocity equation, where Vx is equal to dx over t. Remember, range is just a special dx, and the beginning and ending points of a projectile are at the same level. So I'm going to find Vx, and that would be the cosine of 20 degrees equals Vx over my hypotenuse, which is 15 meters per second. So Vx has a value of 14.1 meters per second. Now, my goal is to find the time. So time is equal to dx over Vx. Remember, dx is just our range, 14.8 meters, and our velocity is 14.1. Make sure it's in the x direction, and I have a time period of 1.05 seconds. That's the total time the projectile's in the air, or in this case, the ball. So it goes from going up to going down. Okay, let's look at part C. What is the maximum vertical distance the ball reaches? So vertical distance, we want dy. So we're going to need to know VIY, which we haven't calculated yet. We do know that gravity is going to act against this, so it's negative 9.8 meters per second squared. So remember, our initial velocity was 15 meters per second. Theta was 20 degrees. And Vy is this initial velocity of the ball. So in this case, we need to use our sine function, and the sine of 20 degrees equals VIY over 15. Remember, we're calling it VIY because it's going to decrease over time because of the acceleration due to gravity, whereas Vx has no acceleration in the horizontal plane. So VIY is 5.13 meters per second. Now, it says, what is the maximum vertical distance the ball reaches? So if you think about the complete trajectory of this ball, its maximum vertical distance is going to have a VFY value of 0, just like we did when we threw a ball straight up in the air. So one of the ways we can solve this is to use the formula that we just used, which is VF squared, in this case VFY squared, equals VIY squared plus 2AD. And I'm going to add some y's in there so we know it's all about y. So I'm going to use this one. There's other ways to do it, but it's just one way. So I'm going to rewrite that equation. That looks kind of messy, and isolate dy. dy is our maximum height. So dy is equal to VFY squared minus VIY squared divided by 2AY. So putting in our numbers, VFY is 0 minus 5.13 meters per second. Again, remember to square it, divided by 2 times negative 9.8 meters per second squared. If you do your math, and we should get about 1.34 meters, which is our vertical distance, maximum height that the ball reaches. So there you go. I'll see you later.